Hi class, welcome to Advantage. My name is Dr. Scott Adamson, and today we're going to look at taking the derivative of a function of the form a to the x, where a is any number greater than 0. The reason I'm saying that is because 0 to the x, for example, wouldn't be all that exciting. Let's talk about exponential functions where we have a base greater than 0 and see what the derivative might look like. So the way we're going to approach this is from the definition, the limit definition of derivative. Let me remind you that that means we're going to take f of x plus h, subtract f of x, and divide all of that by h. So in our case, f of x plus h is going to be a to the x plus h. Minus f of x minus the function itself, all divided by h. Now this is where students sometimes make the error. They say, I'm just going to substitute 0 in for h. And if you substitute 0 in for h, x plus 0 is x. A to the x minus a to the x, 0. Substitute 0 in for h, 0. 0 over 0, indeterminate, we don't know what to do. That would be erroneous thinking. You should be thinking not substituting, but you should be thinking, what happens as h gets close to 0? But before we do that, let's just make one algebraic move. You might recall there's a property of exponents that says if you are adding exponents, that must mean that it came from a to the x times a to the h. That is, if the bases are the same and you're multiplying, the law of exponents says take that base a to the sum of x plus h. If we work that law in reverse, a to the x plus h must be the same as a to the x times a to the h. Now the reason I would make that little algebraic move is now our two terms in the numerator have a common factor of a to the x. So let's factor out a to the x. If we factor out the a to the x from this first term, we're left with a to the h minus, if we factor out a to the x from the term a to the x, we're left with 1. We'll divide all of that by h. Now again, don't do the substitution thing because you'll just end up in the same boat. A to the 0 is 1. 1 minus 1 is 0. H is not 0. H is approaching 0. We're going to have to do some exploration on this limit, but let me just make one more move first. Because h is the variable that's changing here, approaching, getting closer and closer and closer to 0, let's take that a to the x out front so that we can just focus on that limit. A to the h minus 1 over h. Now I'm going to go over to Desmos, I'd like you to join me, and see what happens to a to the h minus 1 all over h as h approaches 0.
We've reached the point in the proof where we have to examine the limit as h approaches 0 of a to the h minus 1 all over h as we examine the derivative of the exponential function a to the h where a is greater than 0. So notice here in red we have created a graph of the function f of h is a to the h minus 1 over h. That's the graph here in red. So we can make a be any base that we like. Now remember, this is not the function just a to the x that we're graphing and thinking about the derivative. We're at that place in the proof of the derivative where we have to examine this limit. So let's say the base was 5. If the base was 5, then that limit as h approaches 0 of a to the h minus 1 over h, that limit would be, look at what I've done here. I've entered in the point 0.000001 to kind of get at that idea that h is really, really small. And then to show you the output of that function, I have f of 0.00001. So here in purple we see that. And I did it so we see both sides of 0, the positive side and the negative side, so that you're thinking about the two-sided limit. Now over here in the graph, Desmos is doing some rounding. It's really 0.000001. Desmos is rounding that to just 0. But please keep in mind that it's not. If I zoom in close enough, you would see that that point is really 2 points on either side of 0. You're starting to see it about now. So there it is. But let's go back out So you can just examine and think through with me what happens as h approaches 0 to a to the h minus 1 over h for different bases a. When a is 5, that limit is 1.609. When a is 8, that limit is 2.079. When a is 1.3, that limit is 0.262, etc. Now, just to connect, if you've already seen the video on the derivative of e to the x, what if the base was e? When the base is e, that limit comes out to be 1, as we saw in that proof. But if the base is not e, the base is a number other than e, and let me just give you some options here to see, then we see that that limit is other than 1. But there is a neat connection I'd like you to see here, just kind of not a formal mathematical proof here, but just an observation using the technology of Desmos. Notice that with our h value being sufficiently close to 0 to see the evidence, the function is outputting these limits, 1.757 in the case of a base of 5.8. But just for observational sake, I'm also having you consider, what about the natural log of 5.8? Interestingly, the natural log of our base produces the same value as the limit that we're exploring. Yeah, that limit as h approaches 0 of a to the h minus 1 all over h produces an output that's equivalent to the natural log of that base. Whoa. Now we can see that again if we go back to the case of e, if you've seen that video. In the case of e, the limit is, as h approaches 0, the limit is just about 1, or the limit is 1. As h approaches 0, e to the h minus 1 all over h approaches 1. And notice the natural log of e is indeed 1 as well. So yeah, that limit is the natural log of the base. And again, for bases other than e, we can see, we can see that the limit is the natural log of a. Boom. Let's go back to the board and see how that wraps up our proof.
So as you've seen on Desmos, as h approaches 0, this limit here does not approach a nice simple number like 1, like in e to the x. It depends on the base. As h gets closer and closer to 0, this limit gets closer and closer and closer to a value that depends on the base a. But the special thing you saw on Desmos is this limit does get closer and closer and closer to some number, and that number is the natural log of a. And so what we figured out is if you had a function of the form f of x equals a to the x, where a is a positive number, then the derivative of that function is going to be a to the x times the natural log of a. Now you can connect that back to, remember e to the x? The derivative of e to the x was e to the x, and we could say times the natural log of e. But the natural log of e is just 1. We typically don't say that. We'll just say the derivative of e to the x is e to the x. But if your base is not the natural number e, if it's some other base, then we're going to have to be sure to include the derivative of a to the x is a to the x times the natural log of a.